Hello. Today we are going to discuss the Edexcel AS level topic of waves. It's coming in your Unit 2 exams, and in this Unit 2 we have both waves and electricity portions. So in this section we are going to discuss the introductory portions of this waves. So it comprises only first few topics on your syllabus. Okay, so we all have a bit idea about what is waves and what are the forms and etc., since we have studied on your IGCSEs. So here is also I'm repeating some of the data with some extra points. Okay, and after that I'm going to discuss the topic wise questions related to this waves. Okay, so first we know what is waves is an energy transfer method. So how the energy is transferred from one place to another. We have like different methods, and one of the method is through the waves. So sound is a waveform, we know that. Light is a waveform, we know. So these are like different types and all. So first we need to have a bare idea of what is wave. That a wave is a means of transferring energy via oscillations. We have oscillations, up and down, vibrations. Due to that vibrations we are transferring the energy. So if there is a loudspeaker is playing, which means that that sound energy is transferred from that loudspeaker to our ears. Okay, so how the energy is transferred from that place to to another place. How the energy is transferred by some vibration of the air particles. That is called the oscillations. That way of transferring energy is what we call the waves. So the energy moves from one place to another without the movement of any matter. So the matter is not moving, but it is vibrating. So as it is vibrating, it transfers the energy to the neighboring one. So the neighboring one is also vibrating, energy transferred to the other neighbor one, so on. So that's how the energy is transferred. And we have like two types of waves especially, that is mechanical wave and the electromagnetic waves. So mechanical waves, which means that which is cannot move through vacuum. So one type of waves will be moving through vacuum, another type cannot move in vacuum, so it needs a medium to travel. So that type of waves are we calling this mechanical waves, okay, which are not needing any medium or material to move or propagate, is what we call the electromagnetic waves. So we have mechanical waves and electromagnetic waves. So that's how we basically classified these waves into two. And we know that according to the wave vibration we have another form also, like the transverse and the longitudinal one. So the transverse and longitudinal ones are categorized according to the movement of the particles in that medium, or like without the medium. So the electromagnetic waves, which is able to move in vacuum, is only a transverse wave. It cannot be a longitudinal wave. So longitudinal waves always needing a medium. So the mechanical waves are of two types, like transverse and the longitudinal. So we are going to compare these two, like what is the transverse wave and what is meant by the longitudinal wave. So in this transverse waves, the particles, like you can take the example of a surface water waves, so which is really common. So let's consider a pond or a beaker of water, something. So it is when it is undisturbed, it will be in a smooth plain surface. Okay, so when we have put some disturbance in that medium, you could see some waves are forming from that point. So if you are throwing any stones to that pond of water, what happens? From that point the waves will start to propagate, which means that from that position to the other parts of this medium, the energy of that stone is transferred in the form of waves or in the form of oscillations. It is vibrating. So how the particles is moving, how the particles is vibrating according to the wave propagation, that is making a difference of transverse and the longitudinal wave. Like here, so if you have thrown the water stone on this water on this position, what happens, the particles, these red line are having the water particles. Okay, so the each water particle will be vibrating in this way, right? In this way will be the oscillations, which is perpendicular to the wave direction. So these type of waves is what we call the transverse waves. So the wave direction is perpendicular to the vibration direction. So vibration direction is up and down, while the direction of movement will be left to right, or right to left, doesn't matter. Anyways, it will be perpendicular to each other. And in this transverse wave, we have the crest and trough. So the upper portion is what we call the crest, the other portion is what we call the trough. So you can see this transverse waves in water waves, the waves on a string, and the electromagnetic waves is also a transverse wave. So in electromagnetic waves, the electric and magnetic waves will be perpendicular to each other and to the propagation of the wave direction. So in the case of longitudinal waves, there is also the particles are vibrating, but the movement of the particles and how it is related to this wave propagation is different from the transverse waves. So here the wave direction is parallel to the vibration direction. So this is one of the example for the longitudinal wave is this sound waves, so which is really common one. So let us suppose here is a loudspeaker. Okay, you have this paper cone on this loudspeaker, which you will be really familiar of, and this loudspeaker will be vibrating like this to and fro, right? So when it is moving in this direction, the wave that air particles will be making compressions, okay, and it will be propagated in this air, and when it is moving on the other side, there will be a low density region which is called the rarefactions. So it's making continuous compressions and rarefactions, and it will be moving in this direction. So if here the loudspeaker is here, the waves will be in this direction, left to right. So how the particles is vibrating like this, okay? So when it is that paper cone is moving in this direction, and when it is in outward inward direction, outward, inward, so the particles will be vibrating in this direction, and the vibration is like transferred in this air particles by using the air particle vibrations. So the vibration is parallel to the direction of wave. So these type of waves is what we call the longitudinal waves. So here is one of the example, loud sound waves, and another example is seismic waves. So basically the seismic waves is basically the waves which is causing the earthquakes. So earthquake, which means that the earth is shaking, or the particular surface is having some vibrations. So it is formed by the rocks cracking under the earth like this. The point where that point is what we call the focus, where the rock is underground rocks is breaking, okay? So from that position, the waves will be starts to move to the surface. So that position is what we call the epicenter. So from that epicenter, the vibrations is moving. So many types of vibrations, waves are forming from that epicenter. The basic waves are the S wave and the P wave. So P wave wave, which means that the primary wave, S wave, which means that the secondary wave. Okay, so here the S wave pushes and pulls as it travels. So the vibration, the earth, that crest, earth is having different layers, right? So here the crest will be moving, the earth surface layers will be moving like towards the epicenter and away, like to and fro to this particular point. And you know that the waves is propagating in this direction upward, and the vibration is in this direction. So what kind of wave it is? It is a longitudinal wave. So it will be like this primary wave, or you could call it as the seismic P wave. So it will be vibrating in this direction, and it is causing high density region and the low density region, which is what we call the compressions and rarefaction. So this type of waves is an example for the longitudinal wave, right? So we have another form also, which is starting from the epicenter to the earth's surface. So this is the wave direction, but the vibrations is like this, which is perpendicular to the wave direction. So these type of waves is what we call the transverse wave. So what we can conclude, this S wave or the secondary seismic wave is a type of transverse wave which is causing more damages to the buildings or the surface. So the S wave shakes from side to side as it travels. So these waves is also you could write in your exams as an example for the transverse and the longitudinal waves. So the next thing is how we are graphing the waves. So we can graph both the longitudinal and the transverse waves using the graphs. So basically we have two types of graph. Okay, so first one is the distance and displacement graph. Okay, so here is the distance traveled of this wave. Okay, so it is having the wave at an instant. So let's consider here examining the cross section view of the water waves. Okay, so you have in front of you beaker of water, which is like a transparent beaker, right? So and you are making waves on this water surface, and you could see the waves is forming, how the waves is forming in that beaker, right? So you could see that there is an equilibrium position where is no disturbance at all, and the vibrations would be like this. You could examine over time, right? So if you are graphing the waves, we can use this displacement distance graph for a particular instant of time. Okay, so at a particular instant you're you're just imagining that you're taking up a picture of the cross-section view of this wave, then it will be like this only, right? Like this. So in here, as you know, the x-axis is represented by the distance traveled. So this length from one crest to another crest, or one trough to another trough, or the similar points on the next wave. So this whole thing is considered as one wave, second wave, third wave. So this is the three waves represented in this picture, right, in this graph. So from this position to the same point on the next wave, this distance is what we call the wave length. What is the length of the wave? That is represented by the crest to crest or trough to trough, the distance. Okay, so the distance traveled by one wave is called the wavelength, and it is measured in the meters only, right, because it's a length. And the displacement, see the particles in the case of water surface water waves, the particles, some of the particles are at higher displacement, some of the particle has no displacement at all, some of were at the opposite, in the opposite direction, a particular displacement. Anyways, there is a displacement or no displacement, right? So what is the maximum displacement? Okay, so from this is the equilibrium position. From this equilibrium position, the maximum displacement is to the crest point and to the trough point, right? So this length from the equilibrium position to the highest point, to the crest or the trough, okay, this is represented by the the amplitude. So the largest displacement in that wave is represented by the amplitude, and it will be having a symbol of capital letter A, and it is also a length, right? The displacement, which is a length, so it is measured in meters only, right? So from the displacement distance graph, you could determine the wavelength from the x-axis and the amplitude from the y-axis, right? So the displacement of the particle is varying at that point of time, because as the time changes, the displacement, maybe the first this particle, now it's at the crest, maybe at the next point it will be at this position, and at the next second it will be at the trough position, right? So it will be varying. So that's how it changes, the displacement distance graph and the displacement time graph, because this one is represented for a single particle. In this case, it will be having like a lot of wave particles, right? But in this case, only a single particle movement or oscillation is represented in this displacement time graph. So there is a change in this x-axis. Here is the time, which is measured in second, okay? In the y-axis, it is the displacement that is measured in meter. So here the y-axis representation of the amplitude stays the same, because it's representing the displacement. The largest displacement is represented as the amplitude, but on the x-axis, the time taken is represented, so it won't be giving you the wavelength value, but the period value. Period is the time for one wave, right? So the particle, this is for a single particle, so the single particle will be taking like this much of time to create another wave. So what is the time for the one wave? That is the period, and it is represented by this length. So here this length is represented by the wavelength, since it is the distance traveled, but here, since it is the time axis is given, this length, the same length, but it is representing the period. That is the time taken for one wave, right? So it is measured in the seconds, okay? So it will be in seconds only, and that's how the two graphs are varying, and you should be having the idea of how the displacement time graph and the displacement distance graph for attending some of the questions. Anyways, we'll be discussing the topic wise question later to that, so you'll be anyways figuring out what are the points and all. So the next point, as you know how the graphs is representing the waves, and the waves are of two types, transverse and longitudinal waves basically, right? So the transverse wave, we have actually discussed the transverse wave till now, like the water waves is a transverse wave, right? But in the case of longitudinal waves, it's a kind of like a confusing part. There is a confusing part in this displacement distance graph, so you must be really careful while you're dealing with the longitudinal waves, and the idea has to be really really clean, okay? So here let's consider, so the distance and displacement graph. So you know, this is for a number of wave particles, a lot of particles that we are considering, but at a constant time, right? So initially the rest position, or you could say the equilibrium position, will be like this. So the dots are given like red, green, blue, black likewise. So the rest positions is really important, and if the particle that let's consider these points are representing the air particle, right? So the movement in the air particle is what we call the sound waves, which is creating the sound waves, which will give you the sound waves. So so what we can do is consider the equilibrium position and the position of the particle on the wave. So the particles will be vibrating to and fro to its rest position, like this. If this point is what I'm considering, okay, so what this particle will be moving like this only, okay? So at a particular instant that I'm considering of, this particle, the first one stays in the same, but the second one is moving towards this position, and the third one stays the same, but this fourth one is moving on the opposite direction, and the fifth one stays the same. So the alternating particles are moving, okay? So this position, this point is the same, but the particles on the other two positions, okay, other two sides are moving towards this point, right? So let's consider this point, this green one, the black and the blue one, both are coming to this particular position, so it's creating a high density on that point, which what we call as the compression. So it is also creating a low density region on the other side, which is called the rarefactions. So you could see that there is a compression happening here, and equally there is a rarefaction in between the compressions. So we could see that some of the particles is moving from its position, which means that it displaces, right? Some of them are not. So here it's given a displacement distance graph. So this point, okay, so where the compression is occurring is at a position where the particle is having no displacement at all, right? Because the other particle is coming towards that point, creating a compression and the rarefaction on the other side. So the positions where the compressions and rarefactions is happening is of zero displacement, right? So this position which is having zero displacement, this position zero displacement. So where are the compressions and rarefactions? At that point the displacement would be zero. Okay, and after that you could see that in this case, okay, for the second one, it displaces from its mean position to a maximum one, right? So here we are considering only a number of particles, okay, in between there will be a lot of particles. Here for our simplicity we are considering only one particle in between the compressions and rarefaction, okay? So this particle will be having a higher displacement, okay? So in the direction to the left, okay, so the left direction we are considering at the bottom, negative displacement. So at the bottom there is a a larger displacement, and for this particle which is having a higher displacement, but it is towards the right side, right? So the displacement is on the positive direction, and here on the third particle this is moving towards the left side, so it is at the bottom, and for this particle it will be on the positive direction. That's how the displacement distance graph is drawn for a longitudinal wave. So you should be memorized that the compressions, rarefactions are formed where the particles are of zero displacement at that point. So the particles on either side of it is moving towards that point, creating a compression, and the rarefaction on the other side. So here the same, the displacement and distance graph will give you the amplitude and the wavelength values, so you could determine that one also, right? So here you could find if the compressions and rarefactions, these points is not given, suppose, okay, so we don't know which one is the compression, which one is the rarefaction, and we have to find out. Then you should be considering in this way only. So here it's considering the particle is moving on the left side, here it's considering the particle moving on the right side, right? So the particles are moving away from it, so this point would be of rarefaction. It is showing the rarefaction point, okay, where the rarefaction is happening. But at this position the particle is moving towards the right side, right? So right side, and here it is moving on the left side, right? So the particles is moving on the towards the same position, here the right side, here the particle is on the left side. So at this position it will be compression, okay? So if it is going like this, then at this zero displacement point would be rarefaction. If it is going like this, the zero displacement point will be representing the compression. That's how you need to find out the compression and rarefaction point, okay? And so this one is for the wave particle. So the sound waves you could be considering as the pressure wave, because the wave, the air particles is forming due to the pressure variations. So this one is the undisturbed air, so each particle is having like a particular position in this space. So when there is a sound wave present, the air particles will be forming compressions and rarefaction, and it will be changing, okay? This is for a particular time. So here you could consider consider that this point is of high densities and these are the points are of low density. So you could represent the sound wave in terms of pressure wave. Okay, so the solid line is representing the pressure. So you know that here at this point where the compression, so the pressure would be high. So here the y-axis is representing the pressure. Okay, the x-axis is representing the distance. So high pressure, then it's a low pressure here because it's the rarefaction. High pressure, low pressure, high pressure, low pressure. This is how the pressure distance wave would be for the sound waves or the longitudinal wave we could see. But here if you are considering the like the displacement distance wave, you know that at the point of compression, the center for the compression would be of zero displacement. So here in this case the y-axis is representing the displacement. So zero displacement, it is downwards. So this is showing you the compression. So it's upwards. So this is the rarefaction. Downwards, compression point, rarefaction point, compression, rarefaction. So there's a change in the pressure distance graph and the displacement distance graph as well. That's why I told you the longitudinal wave representation is a bit complicated, but once you got the idea of how the waves is formed, it is simple. So that's it for this this session for the first few topics on your syllabus, and then in coming video we can discuss the topic questions related to these data as well. So it will be having like 10 questions related to that. It will be having both the MCQ and the like the theory questions as well. Thank you.